Hi, Mick McQuaid here for iste782 Visual Analytics. And today I'd like to give you a very brief lecture on relational data. This is chapter 10 of our textbook, R for Data Science, and part 2 of the textbook. So our textbook offers a chapter on relational data. Everyone taking this course is required to have at least a one-semester database course. So the textbook uses terms differently from the way they're used in our relational database courses, but it should be easy to map the terminology to familiar concepts. The goal with this chapter is simply to be able to join tables and do some basic set operations using the dplyr terminology. Dplyr is the package that's part of the tidyverse that we're using to do this. And you may wonder why I pronounce it dplyr. I have no idea. I just made that pronunciation up. I've never actually heard Hadley Wickham or Garrett Goldman speak, so I have no idea how they pronounce it. Okay, now to do this, we're going to need to load the tidyverse, and we're also going to need to load what is essentially a relational database, NYC Flights 13. So this is a package, a library, that contains about 5 data frames. In fact, here's a picture of the data frames arranged as kind of an entity relationship diagram. So the 5 data frames are airports, planes, flights, weather, and airlines. And each one of them can be quizzed. So once you've loaded NYC Flights 13, you can type $airports or $planes or $flights and find out the structure of these tables. And you can just type in their names to actually see the first few rows of each of these tables. And this is really excellent data. By excellent data, I mean that it's very clean data. It's got it's well-formed data. Let's put it that way. And what this sort of entity relationship diagram type thing shows us is the links between the tables. So for example, and the ellipses, I should mention, indicate that there are more fields in each table. So if you type $airports, you'll see that there are about 8 fields in this. So the only reason that we're only showing FAA is because that's the only one that we're actually using in our relational database exploits today. FAA is just a 3-letter abbreviation for the airport. For example, Rochester's airport's abbreviation is ROC. And it shows up in 2 columns of the flights table. The origin, which is always going to be LAG, EWR, or JFK. Those are the New York City airports. And destination. So this is a database of flights, about 336,000 flights, something like that. All the flights that originated from one of the 3 New York City area airports in the year 2013. And so the FAA abbreviation appears in 2 columns here, giving the origin and destination of the flights. The planes, there's a lot of information about the airplanes. The only thing that appears in here is the tail number of the airplane, which is enough to identify this. So the tail number is unique. The FAA abbreviation is unique. This combination of year, month, day, hour, and flight is allegedly unique. This combination in the weather table is unique. And airlines, there are like 16 airlines represented with 2-letter abbreviations, which are unique. Okay, so that's the NYC Flights 2013 data. And we're going to use that with some database operations. And the unit of analysis in this chapter is pairs of tables. So we're going to use pairs of tables or pairs of data frames, or pairs of tibbles, as the authors like to call them. The authors posit 3 purposes of verbs. So there are mutating joins, filtering joins, and set operations. And that's the remainder of what we're going to talk about. Is we're going to go through each one of these 3 in turn. So mutating joins add variables from one tibble. A tibble, recall, is a kind of data frame to matching rows in another tibble. Filtering joins remove observations from one tibble that do not match observations in another, and set operations treat observations as set elements from set theory that you may be familiar with from math or philosophy, logic, other courses. Okay, so the first one is mutating joins, and these joins all combine variables from two tables. So they include an inner join, a left outer join, a right outer join, and a full outer join. And you should be conceptually familiar with these from your database course that's required, and possibly more than one database course you may have taken. And the authors use this attractive diagram to explain the inner join. So the colored dots signify the matches. So the green dot signifies a match between x1 and y1. The purple dot signifies a match between x2 and y2. So the result of the inner join is this table that contains x1 and y1 and x2 and y2. And there's this key field that contains 1 and 2. It's the key field that joins them. Now, I'd like to show you an R language version of what you just saw as a diagram. So remember that a tribble is a row-wise tibble. Of course, it's really a thing from Star Trek, but they're using the name here for other purposes. So it's a row-wise kind of data frame, and this has two columns, one column called key and one column called val x. And this one has two columns, one column called key and one column called val x. And you notice that these two have two keys in common and one key that's not in common. So here's x and here's y. So if I try to do an inner join between them, I get a resulting tibble, which is the two columns where the two rows where the keys matched. Oh, and I said by key here. This is not strictly necessary because by default, R is going to assume that two columns with the same name are what you want to join by. But I've said it anyway. This is, and there are cases where you're going to need to say it. We'll see those in a minute. Here's an example of a left outer join. So the red dot here signifies a row that's included without a match, hence NA. So the left outer join includes all of the records from the left table and all the matching records from the right table. So there was no matching record for x3, so we just have NA there. And a right outer join is simply the mirror image of the left outer join. So we include all of the right table and any matching rows from the left table, and we just get NA for y3. A full outer join includes all of both original tables. So we're going to include all of this one and all of this one. And for the rows that don't match, we just have some NAs. So this is each kind of mutating join: an inner join, a left join, a right join, and a full join. And I've put in by key here. By key is not strictly necessary. If you've got two columns with the same name, you could just say inner join XY. In fact, I think the next slide, yeah, this slide shows us. The default is by equals null, and it matches on all columns with matching names in both tables. By some name, which is what we've done, is sometimes useful. An example of where this is useful is that year has a different meaning in the flights table than it has in the planes table. So in the planes table, it's the year of manufacturing of the planes. In the flights table, it's the year that the flight occurred. So we don't want to use it to join those two tables. Otherwise, we wouldn't get any matches at all, because presumably the planes were manufactured before they flew. So we suppress its use by saying by tail num, if we want to join the flights table and the planes table. And the other thing we can do, so sometimes we'll have the situation where we have two names that differ, but they mean the same thing. So, for example, the FAA name in the planes table has the exact same meaning as the dest column in the flights table. I'm sorry, did I say the planes? I meant the airports table. So we join the airports to flights, and these two are the same. These two have the same meaning. And here I could have said by equals C, but I don't have to because this is the default position for this. So the default is the left table followed by a comma, followed by the right table, followed by a comma, followed by. So I can just give their positions, but I can also specify them by names. Okay, so on to our second of three topics, the filtering join. The filtering join is simple. These functions affect rows rather than columns. You could also think of them as affecting observations rather than variables if you come from the kind of experimental science background that uses those. We typically say rows and columns in databases. So anyway, the semi-join keeps all the observations in X that have a match in Y, and the antijoin drops all the observations in X that have a match in Y. And we have diagrams to show these two. So here's a diagram showing that we've kept so this is, like kind of like an inner join, except that we're only keeping what's in X. And here again, we're only keeping what's in Y. Oh no, I'm sorry. This is the antijoin. So I thought I had another semi-join here, but this is the antijoin. So I'm only keeping what's not in both in the antijoin. Okay, and then last are set operations. So these should be familiar to you from math classes, intersect or logic classes, or some kind of classes. Intersect returns observations that are both in X and Y. Union returns unique observations in X and Y. And by unique, all I mean is not duplicates. So it returns all the observations, but without any duplicates. And set diff returns the set difference of X and Y. And these operations expect the same columns in X and Y, and they treat the rows like sets in set theory. So here's an example. Here's a pair of triples P and Q, and P and Q both have a row in common. So 1, 1 is the same in both, but row 2 is different. Row 2 does not have a match in them. So if we do the intersection between the two, intersect PQ, we just get row 1. If, on the other hand, we do the union, we get row 1 and row 2. But we only get one copy of row 1, so we get no duplicates of row 1. The set difference, there are actually two set differences. So there's the set difference of P given Q. So this contains the what's in P that's not in Q. And then there's also the set difference of Q given P, which contains what's in Q that's not in P. And that's it. That's all there is to this chapter. These database operators can give you some of the same functionality as SQL. If SQL is available, I would typically use it in preference to these techniques because it implies that the data is dynamic. And by dynamic, I mean that the database is live, that the results you get from one query may differ from the results that you get from another query a few moments later because the data is being updated. And you always want the most updated data. Even if the data you want is old, you may want corrections that are reflected in updates. So in general, you want to use the database as the source of ground truth. But you may receive static files, or you might receive database files that are disconnected from a live database for analysis. So these operators may be helpful, especially in generating reproducible research. And reproducible research is an important topic. Reproducible research is not something we cover in this class, but it is covered in this textbook. So the latter chapters of the textbook are a lot about reproducible research. It's very important for data scientists to know about. And finally, these operators can be helpful in maintaining flow. So if you've already started using R on a data set, when you realize you need relational operators, I personally would not take the data out of R and put it in a relational database just to use some relational operators. I would, if the data is already in R, I'm going to continue with my flow of work in R and use these operators. Okay, so that's all. So thank you very much for your attention. Until next time.